a week ago or so, I was talking about this oscillator, radio oscillator, and I told that I was going to publish the schematic as soon as possible. Well, that took quite a long time after all, but now it's in its final stage. And there is of course a lot to tell. Here you see all the coils that belong to that oscillator. I've all wound them myself. You can surely see it. Lacquered copper wire, some glue to fix it properly, and then to get to all the frequency bands. And they are here. And I wanted to be absolutely sure that the circuit was reproducible. So I made it again and found that I could not, at first, get out a pure signal on the gate. And finally I found that this capacitor here, this is the schematic, this capacitor here, 10 nanofarad, was responsible for that effect. When that capacitor is small, so you leave it here and you only have here 100 picofarad, the oscillator can go to much higher frequencies, but you cannot take the signal out of the drain any longer. I don't know why. It's simply so that the circuit changes its properties when that capacitor is too small. Furthermore, I found that this capacitor going from the gate to the source, and this capacitor, this combined capacitor, forms a capacitive voltage divider with this capacitor, and they both are responsible for the frequency where the circuit works, but it had to work to maximum approximately 2 megacycles, and that means that when you make this capacitor, these smaller in value, you go to a higher frequency band. That is of course combined with the coil that's connected here. And this is, say, a combined capacitor. Of course you can do the calculations, but I don't do that. It's important to tell that when you add here that 82 picofarad capacitor in series with the 220 picofarad, the frequency goes to approximately 2.3 megahertz. This is also important here, a 10 microhenry coil from the gate to all the other coils and the capacitor, say the tank circuit. Here is the tank circuit connected. This is a tank circuit, by the way. This is the tuning capacitor. And I've made, by purpose, in this circuit, the experimental circuit, I've used 2 capacitors in the tank circuit. So, put down the camera for a while. I want to draw that situation. I now draw all the coils. So, here is the tuning coil. And here's the tuning capacitor. And here is that I've connected here all kinds of microhenry coils to look at the frequency that can be reached. And it reaches now between 8 between 237 kilocycles up to 2.3 megacycles. So when you connect a coil of 28 microhenry to the input of this oscillator, this one here for instance, 28 microhenry, and you have a capacitor here of 22 picofarad, the maximum frequency is 2.35 megacycles. And of course you can connect here a tunable, a variable capacitor. That means that you can say set the frequency in a certain frequency band. It's very interesting to do all these experiments. I can advise to wind some coils, find some ferrite material, etc, etc. Take your scope and your counter, that's what you need for this circuit. And well, then you can find out all the frequency bands and make this oscillator suitable for your application. That's very important, of course. Furthermore, I take the signal now out of the drain. That's a little bit uncommon anyway. With these two different resistors you can lift up the output level a little bit. Output level is between 0.3 and 0.5 volts. Schematic again. And the frequency table again. I think that's also very important. So when you study this table, you can surely find how to make this oscillator suitable for a certain application in the frequency band between 237 kilocycles and 2.3 megacycles. When you want to get that frequency band, use this schematic. Especially here, this set of capacitors, this capacitor, and here the 10 microhenry input coil. How does a 10 microhenry input coil look like? Well, this is one 10 microhenry. You can buy these coils in electronics shops. You can also buy in electronics shops all kinds of other coils. Here's some examples in different values. It is somewhat better when you want to do these experiments, and then especially when you go to the higher frequencies, to buy these coils on a small ferrite rod, tiny ferrite rod. They are also very cheap, 56 microhenry, 120 microhenry, etc, etc. These coils work also, by the way. They are cheaper. You can buy them via Ali. They also work, but for the higher frequencies the quality factor is sometimes not completely okay, say not high enough, so that the other type of coils is much better. Problem is that I need two hands to demonstrate it all. Now we are on 404 kilohertz. This is a waveform. This broadening disappears when you mount this whole circuit into a metal box. Perhaps I can make some other frequencies visible. be interesting to show. I now show the highest possible frequency. 2.35 megahertz. This is the waveform. Again, this broadening disappears completely when everything is properly shielded in a metal box, etc., etc. Reason that you see it here is that the whole circuit, the oscillator, picks up noise from everywhere. These wires pick up noise, etc. So when you want to make it in a stable way, this is a good idea. And when you can find such a beautiful tuning capacitor, you are a lucky one. I bought this oscillator that originally worked up to 10 megahertz, say 5-6 years ago, but I made a fatal mistake when measuring high voltages with it. In other words, driving a high voltage transistor. And anyway, I had to refurbish it, downgrade it to this circuit, what it is now. Thanks for watching. Pan over somewhat. Again, the frequency table. And in these cases, up to 2 megahertz, you can use normal audio switches to switch the capacitors and coils in and out.